Hey guys, it's Miss Miklos, and in today's lecture we are talking about what we call the binomial theorem. And we've talked about binomials since you were in like pre-algebra, algebra 1, but this is probably the first time that you've actually heard of this concept. So we know that a binomial is a polynomial that has two terms. What we're going to be learning in this section is a formula that gives us a quick way to raise a binomial to a power. So if we take a look at this, we're expanding the quantity x plus y to the nth power. So we're substituting in different values for n. If we substitute 0 in, we get 1 because we know anything to the 0 power is 1. If we substitute 1 in, we get x plus 1. Those are really easy for us. Okay, this second one, we know squaring something means I'm multiplying it by itself. So we would normally write this out like x plus y, there we go, plus, that's an ugly plus, but that's okay, times x plus y, and we would FOIL and we would end up getting this expression. Now, these three aren't that tough, but all of a sudden when I get x plus y cubed, that means I'm going to have to FOIL these two binomials and then multiply it by another x plus y. And we can just see that gets more and more difficult as we continue on. We would have to do more and more work. So what I want to show us, there are actually several observations that we can make about these expansions. Okay, in each expansion there are n plus 1 terms. So what that means is if my exponent is 2, I have 3 terms. If my exponent is 5, I have 6 terms. So we always have one more term than the power. In each expansion, x and y have symmetric roles. Okay, if we notice x, the powers of x decrease by 1, so it's like x to the 6th, x to the 5th, 4th, 3rd, 2nd, 1, and then x to the 0 means it's just 1, so it goes away. And the powers of y increase, so y to the 0, y to the 1st, 2nd, 3rd, 4th, 5th, and 6th. The other thing I want to point out is the sum of the powers in each term is n. Okay, so I think this is best illustrated using the quantity x plus y to the 6th power. Okay, if we look at some of these terms here, I have x to the 4th y squared, so if I add 4 and 2 together, we get 6. 5 plus 1 is 6, 3 plus 3 is 6, and 6 is the n value. And then the final thing that we are going to notice here, so there's a lot to notice, is that the coefficients increase and then decrease in asymmetric pattern. So let's look at this one again. It goes 1, 6, 15, 20, 15, 6, 1. So we notice that the coefficient for the first term is the same as the coefficient for the last term. The coefficient for the second term is the same as the coefficient for the second to last term. The coefficient for the third term here is the same as the coefficient of these terms. So we can see it is symmetric and it goes back and forth. So we're going to use all of these concepts to help us save some time in multiplying these binomials out. Okay, the coefficients of a binomial expansion are what we call binomial coefficients. And to find them, we use what we call the binomial theorem. So the binomial theorem, okay, and this is going to look confusing. I promise it's not as confusing as it looks. But it says the expansion of x plus y to the nth power, and it kind of has all of these terms out. Okay, the coefficient of x to the n minus r, y to the r is, we call this a combination. So we do n combination r. So n is whatever this exponent is. Okay, r is whatever the exponent of the y value is. And what we'll see is that that is actually like the number term it is in the sequence. The way that we find this, there's actually two ways to find it. We find it by doing n factorial over the quantity n minus r factorial times r factorial. We are also going to learn how to do this in our calculator. Often we will see this symbol that kind of looks like a column from a matrix in a parenthesis. This is often used in the place of NCR to denote binomial coefficients as well. So we will see both of those. Okay, so just to review, this n is our total number. And that's always going to be the bigger of the two numbers. Sometimes the two numbers will be exactly the same. Okay, and R technically means the number removed. And in order to get this on our calculator, and I will demonstrate this later, but if you go math and then choose probability, there is an option that says NCR. So I would need to put whatever my total number is first, then choose this button, and then put the number of removed and press enter. Okay, so let's go ahead and look at A. So it says 8 combination 2. So 8 is our n value, so that's going to go in the numerator. And then I need to do 8 minus 2, because 2 is our R value. And then I'm going to do 2 factorial. So if I go through this, I have 8 factorial over 6 factorial, 2 factorial. We learned earlier this chapter, 8 factorial means 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. So I can actually simplify these, and just 7 and 8 are left over. So when I multiply, I get 56 over 2 factorial is 1 times 2, which is 2, and that ends up being 28. Okay, for B, the first thing I'm going to do, I'm going to rewrite this as 10 combination 3, and it's going to be 10 factorial over 10 minus 3 factorial, 3 factorial. So we can think of this as 10 factorial over 7 factorial, 3 factorial. The 10 and the 7 would cancel out to be 8 times 9 times 10. So I have 720 over 3 factorial is 6. So I get 120 as my answer. We will learn later how this actually corresponds with what we're going to do. Okay. Right now we're just really practicing this concept. So 7 combination 0 would be 7 factorial over 7 minus 0 factorial, 0 factorial. So I have 7 factorial over 7 factorial, 0 factorial. We know these are exactly the same, so I can just cancel them out. And we learned the other day that 0 factorial is equal to 1. So what I want us to know is that whenever r equals 0, our answer is always going to be 1. Okay, for D, we have 8 combination 8. So when I do this, I have 8 factorial over 8 minus 0 factorial. I'm sorry, not 8 minus 0. 8 minus 8 factorial. 8 factorial. I was jumping ahead and knew that that was going to become 0. So I have 8 over 0 times 8. The 8's cancel out, and once again, I am left with 1. So whenever our n and our r values are the same, we also get a value of 1. Okay, our last two here, 12 combination 4, I'm going to do 12 factorial over 12 minus 4 factorial, 4 factorial. So I get 12 over 8 times 4. So this would become 9 times 10 times 11 times 12. So that would be 11,880 divided by 4 factorial is 24. And when I actually divide these, I end up getting 495. Okay, so hopefully we are getting the hang of this. F, I don't know why I wrote a C there. I meant to do 100 combination 2, which would be 100 factorial over 100 minus 2 factorial 2 factorial. So this one seems really rough, but what we're going to notice is a lot of stuff cancels out. This just becomes 99 times 100. So I have 9,900 divided by 2, and 9,900 divided by 2 is 4950. So that's how we go about finding those binomial coefficients. Now let's actually figure out how we're going to use that in our overall problem. Okay, so now we're actually going to go through the process. And there's really, I guess, 4 different steps. So the first step is we need to go ahead, and let me zoom in here so it's easier for me to write. We need to start by finding all the coefficients. Now, if we look at this, our n value is 3. So if n equals 3, we said that there's always one more term than our n value. So that means that there are 4 terms. So what we are going to end up doing, we're going to find what is 3 combination 0, 3 combination 1, 3 combination 2, and lastly, 3 combination 3. Okay, so those are the coefficients that we need. Now this first one, we said whenever we have a 0 there, we know that the value is 1. In the very beginning, we said that the coefficients are symmetric, so if my first coefficient is 1, my second coefficient is also 1. Okay, next we have 3 combination 1, and I'm going to do this off to the side, so I would do 3 factorial over 3 minus 1 factorial, 1 factorial. So that would give me 3 factorial over 2 factorial, 1 factorial, which is just 3. So that means that my other coefficient is also going to be 3 because these always go in a symmetric pattern. So I'm going to go ahead and space this out, and I'm going to write my coefficients. 1, 3, 3, 1. Okay, so I'm really spacing that out here. The next thing I'm going to do, I'm going to pay attention to this first term. Okay, we saw that this first term always starts to the nth power and decreases by 1 each time. So I'm going to write x cubed, x squared, x to the first, and then x to the 0 power. My second term is going to start to the 0 power and then increase. So 1 to the first power, 1 to the second power, 1 to the third power. Okay, so just kind of to recap here, let me zoom out. The 3 things that we've done, we figured out the coefficients. We took the first term and made it decrease every single term. We took the last term and made it increase every single term. So our final step here is going to be to add these terms together and simplify. So this first one, I have 1 times x cubed times 1, which is just x cubed. 3 times x squared times 1 is 3x squared. 3 times x times 1 squared is 3x. And 1 times 1 times 1 is 1. So our answer would be x cubed plus 3x squared plus 3x plus 1. And you guys might be thinking, wow, that took way too long to do this one problem. But what we will notice is the better we get at this, the quicker it is. And it actually does take a lot less time than multiplying all those binomials out. Now, if you did multiply out x plus 1 times x plus 1 times x plus 1, you would get this as your answer. Okay, for B, notice I have 3 again, so the good news is we already know that our coefficients are 1, 3, 3, 1. My first term is x, so I have x cubed because our n is 3, x squared, x to the first, x to the 0, and negative 1 is our other term. So I have negative 1 to the 0, negative 1 to the first, negative 1 squared, negative 1 cubed. So I have 1 times x cubed times 1, which is x cubed. 3 times x squared times negative 1 is negative 3x squared. 3 times x times 1 is 3x. 1 times negative 1 is negative 1. Okay, so even though every single one is going to be slightly different, we are following the same exact steps every single time. Okay, so if we look at C, once again we notice we have an n value of 3, which means that this information still applies. Okay, so we're going to have 4 terms again, and we know our coefficients are going to be 1, 3, 3, and 1. So this time, my first term is x, so I'm going to do x cubed, x squared, x to the first, x to the 0. My second term is y, so I have y to the 0, y to the first, y squared, and y cubed. So when I go ahead and simplify this, I have x cubed plus 3x squared y plus 3xy squared plus y cubed. And once again, we would get the same exact answer if we FOILed or multiplied all 3 binomials together. It just takes a little bit longer. And the higher the n value gets, the longer it takes to do that. So D, once again, I have 3 as my n value. So I have 1, 3, 3, 1. X is going to be x cubed, x squared, x to the first, x to the 0. Negative y, so negative y to the 0, negative y to the first, negative y squared, and negative y cubed. So negative y to the 0 power is 1, so I just get x cubed. 3 times x squared times negative y would be negative 3x squared y. 3x times negative y squared would be y squared. So I would have plus 3x y squared. And lastly, 1 times, when I cube negative y, I get negative y cubed. So moving on here to example 3. This time, we notice that we have a slightly different value here. We have 4. Okay, so I'm going to start, let me kind of zoom in again here. The n value of 4 tells us that we are going to have 5 terms altogether. So we need to start by finding 4 combination 0, which we know automatically is 1 because we said anything that has a 0 here is 1. Okay, 4 combination 1, 4 combination 2, 4 combination 3, 4 combination 4. Okay, I know that last one is also going to be 1 because these go in a symmetric pattern. So if I do 4 combination 1, that means I would have 4 factorial over 4 minus 1 factorial times 1 factorial. This reduces to just be 4. So I know 4 combination 1 is 4, 4 combination 3 is also 4. Now for 4 combination 2, I would get 4 factorial over 4 minus 2 factorial, which is 2, 2 factorial. So when I simplify this, this would be 3 times 4, so I have 12 over 2, which is 6. Okay, and once again, we can also find these by using our calculator, which I talked briefly about, but I'm going to demonstrate that at the very end of our notes. So, our coefficients go 1, 4, 6, 4, 1. So I'm going to start here, 1, 4, 6, 4, and I'm making this one big, 1. Okay, so now we're going to follow the same exact thing we did last time, except this time, my first term is 2x, and our end value is 4. So I'm doing the quantity 2x to the 4th power, the quantity 2x cubed, the quantity 2x squared, the quantity 2x to the 1st, and the quantity 2x to the 0 power. My second term is -3, so I have -3 to the 0, -3 to the 1st, -3 squared, -3 cubed, and -3 to the 4th. So this time, we have a little bit more work to do, so I'm going to write it all out for us. I would have 1 times 2 to the 4th is 16x to the 4th times 1. So that would give us 16x to the 4th. My next one would be 4 times 2 cubed is 8 times x cubed times -3. When I multiply those together, I get -96x cubed. Next, I have 6 times 4 times x squared. -3 squared is 9. When I multiply those together, I get 216x squared. 4 times 2 times x times -27 gives me -216x. And lastly here, I get 1 times -3 to the 4th is 81. So I have plus 81. So my final answer is this polynomial. Okay, now I want to point out that, notice we said that our coefficients are symmetric. Here they don't look symmetric. However, in the way that we originally set this up, this 1, 4, 6, 4, 1, those are what are symmetric. Okay, so our final answer may not look symmetric in its details, but that's totally fine. Okay, for B, we have x minus 2y to the 4th. So once again, we already said our coefficients are going to be 1, 4, 6, 4, 1. Okay, my first term, x. So I have x to the 4th, x cubed, x squared, x to the 1st, and x to the 0. Okay, so our first term, we start at the highest degree, which is n, and we decrease. Our second term here, -2, y. We start with the 0, and we increase each time. Okay, so hopefully at this point, you guys are starting to really understand this pattern. So notice there's not really that much for me to memorize. It's just a knowledge of what to do as I'm going through these problems. So now let's simplify these. Okay, I have 1 times x to the 4th times 1, which is x to the 4th. I have 4 times x cubed times -2 times y, which would be -8 x cubed y. 6 times x squared times 4 times y squared would give me plus 24 x squared y squared. 4 times x times -8 times y cubed would give me -32 xy cubed. 1 times 1 times 16 times y to the 4th would give me positive 16 y to the 4th. So looking at this here, this polynomial right here would be our final answer. I want to note that in our final answer, okay, we do notice that each term has a degree of 4. These terms, these exponents, add up to be 4. Okay, C, we have the quantity x squared plus 4 cubed. So this time our n value is 3. So I'm going to have to do 3 combination 0, which we already saw was 1. 3 combination 1 is 3. You guys might be noticing, or maybe you haven't, but whenever I have a 1 here, our answer is always going to be our n value. Okay, 3 combination 2 and 3 combination 3. We know that this is symmetric, so it would go 3, 1. So I have 1, 3, 3, 1. Okay, so we're starting here x squared. So I have x squared cubed, x squared squared, x squared to the first, and x squared to the 0 power. Now I have my 4, so I have 4 to the 0, 4 to the 1, 4 squared, 4 cubed. And now let's go ahead and do the math. So I have x to the 6th plus 12x to the 4th, because when I'm taking an exponent to a power, we multiply, so that's how we got 6. 2 times 2 is 4, plus 3 times 4 squared, 3 times 16 would give me 48x squared, plus 4 cubed is 64. So this would be our answer. Now notice this time, okay, our terms don't add up to be 3, and the reason being is because one of these terms was not a variable. It was a constant. Our other term had a higher power to begin with, so that kind of made it a little bit different. Okay, D's the toughest one we've gone through so far here. So I need to start off here by finding 5 combination 0, which is 1. 5 combination 1, which is going to be 5. 5 combination 2, 5 combination 3, 5 combination 4, 5 combination 5, which we know is 1, and we know this is 5. So I really only need to find what is 5 combination 2, or 5 choose 2. We can say it either way. So I have n factorial over n minus r factorial, r factorial. Okay, this becomes 3, I'm sorry, not 3. This would become 4 times 5, so I have 20 over 2, which is 10. So these values are both 10. So we know our coefficients are going to go 1, 5, 10, 10, 5, 1. Okay, my first term here, 2x. So I have 2x to the 5th, 2x to the 4th, 2x cubed, 2x squared, 2x to the 1st, and 2x to the 0. Next, I have a negative 3y, so I have negative 3y to the 0, negative 3y to the 1st, negative 3y squared, negative 3y cubed, negative 3y to the 4th, and negative 3y to the 5th. So going through this, okay, this deals with some bigger numbers, so I'm going to write everything out. I have 1 times 2 to the 5th, x to the 5th times 1. So I get 32x to the 5th. Okay, 5 times 2 to the 4th, x to the 4th, times negative 3y becomes negative 240 x to the 4th y. 10 times 2 cubed times x times negative 3 squared times y squared becomes 720 x cubed y squared. 10 times 4 times x squared times negative 3 cubed, or we could just write negative 27 if we want, times y cubed. I get minus 1080 x squared y squared. Okay, 5 times 2 times x times negative 3 to the 4th y to the 4th gives us 810 xy to the 4th. 1 times 1 times negative 3 to the 5th y to the 5th gives me minus 243 y to the 5th. Okay, so this would be our final answer. One thing I want to point out here, we have 1, 2, 3, 4, 5, 6 terms. That makes sense since n is 5 and we know it has to be one term higher than our n value. Okay, so there actually is another way to remember the binomial coefficients. There is something that we call Pascal's triangle. You guys may have heard of this before. It's a triangle named after the famous mathematician Blaise Pascal. So the way that it works is that the first number and the last number in each row is a 1. Every other number in each row is formed by adding the two numbers immediately above the number. Okay, so like here we have 1, 1, 1. Okay, we couldn't really do much. Those are all the outside ones. Now 2, it's because 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 2 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5, and so forth. And what we will notice is that is actually the exact same coefficients as the binomial theorem. Okay, so kind of crazy that we can use that to find the binomial coefficients. The one thing to kind of point out though is that we need to call this the 0th row. So 0th row, first row, second row, and so forth. So if it says like something like this, 5 combination 2, what that is telling me to do is I need to go to, let me actually zoom in on this. This tells me the 5th row. And what can be a little bit confusing, okay, this 2 is telling us to go to the second number, but we need to remember that 1 is like the 0th number. Okay, which that's what's kind of weird. So, 5th row, technically, if we scroll all the way back up here. So, this is the 0th row, first row, second row, third row, fourth row, 5th row. Okay, we don't count this first one. So we go 1, 2. So our answer here is 10 because 4 plus 6 is 10. So we can go ahead and say that 5 combination 2 is 10. And this is something where obviously that seemed a little bit more complicated than just finding, like, using the other method, I guess. But if you're using this on everything, it's really easy to create Pascal's triangle. And we'll practice that again. But if you create the triangle, then you can just refer to that again and again and again. Okay, so last one before we talk about how to recreate the triangle and our calculator. 3 combination 1. So this means third row, first number. So if we go back up here, okay, so we're going to go to the first row, or I'm sorry, the third row. We know that first number doesn't really matter, and so we're going to choose 3. So when I go back to our answer here, it would be 3. So just kind of to review how we would make Pascal's triangle by hand, we start with 1, and we have 1 and 1. Okay, so I have 1. 1 plus 1 is 2, 1. 1. 1 plus 2 is 3. 2 plus 1 is 3, 1. 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, 1. And so forth. Now, when we're looking at the numbers that we're choosing, we're just looking at these numbers that are formed in here, unless we have a 0, and then we're looking on the outside. So we could continue. Our next one would be 1, 5, 10, 10, 5, 1, and we could just kind of see how that continues to grow. So last thing we're going to talk about is how to actually do these combinations in our calculator. So I want to end this lecture just by showing you guys where to find some stuff on your calculator. So if we go ahead and press the math button, I'm going to move over to the probability menu. And notice that that third button down, that third option, is a combination. Okay, so let's say I had something like 5 combination 2. I would type in 5. And then I would go ahead, I don't know why I pressed second, I would press math, and move over to probability and choose NCR. And notice mine automatically makes it into like the little subscript. Some of yours will just say 5 and then it will say NCR and then you would type in 2 and it would automatically tell me that that is 10. So once again, the way that we find that, we go math, probability, and we choose the combination button. So this is another method to find those binomial coefficients. So even though this lecture was a little bit longer, hopefully we really learned the patterns that are going to help us be successful in this particular lesson.